All right, let's jump right into the quantum world today. We're going to be looking at these things called Pauli matrices,
Oh, yeah.
and they might sound kind of intimidating, but I promise you they're really key to understanding. One of the most mind-blowing concepts in quantum mechanics, and that is spin. You see, particles like electrons have this really intrinsic property we call spin, and it's kind of like angular momentum, but like way weirder. To help us sort of unravel this quantum mystery, we've got our expert here with us today.
Hey, it's great to be here.
Yeah.
You're right. Pauli matrices are really fundamental to understanding spin. Think of them as a set of three special 2x2 matrices, and they kind of give us this mathematical language to describe how spin works.
Okay.
They're actually named after Wolfgang Pauli,
Yep.
who was a pioneer in quantum mechanics, and they're essential tools in our quantum toolbox.
So we've got these three matrices, X, Y, and Z. What's so special about each one? What do they actually do?
Well, each matrix actually corresponds to a particular action that you can perform on a quantum system. So take the Pauli X matrix, for example. It acts as what we would call a spin flip operator. It actually changes the spin state of a particle. It's got kind of analogous to flipping a switch from on to off.
Yeah.
But in the quantum world, it flips the spin from up to down or vice versa.
So it's kind of like a quantum version of a not T gate, like in classical computing, flipping bits from 0 to 1. That's pretty neat. What about the Pauli Y matrix? What does that one do?
Yeah, so Pauli Y is where things get a little more complex. It not only involves flipping the spin, but it also introduces this thing called a phase shift. So you can imagine like a spinning top. It's not just about whether it's spinning clockwise or counterclockwise, but it's also about where it is in its rotation. Phase actually captures that rotational information in the quantum world, and it becomes really crucial when we start looking at things like quantum entanglement.
Okay, so it's like knowing not just the direction, but the point in the rotation as well. Yeah, that sounds pretty important. Now, what about Pauli Z? What role does it play in all of this?
Yeah, so Pauli Z basically acts like a measuring stick for spin. It tells us whether a particle's spin is up or down along a specific direction, which is typically the z-axis. It's kind of like using a compass to determine which way a particle is pointing in terms of its spin.
So we've got these three matrices, and each has its own sort of unique personality when it comes to manipulating spin. Why are these matrices so powerful mathematically? What makes them tick?
Yeah, so what makes them really remarkable are their unique mathematical properties. For example, they're what we call non-commutative, meaning that the order in which you multiply them matters, unlike with regular numbers.
Okay.
And this reflects a very fundamental principle in quantum mechanics, that the order of operations can actually change the outcome.
So unlike 2 times 3 being the same as 3 times 2,
Yeah.
with these matrices, the order really makes a difference.
Exactly. It really highlights this inherent weirdness of the quantum world. Another really crucial property is that they have specific eigenvalues and eigenvectors. And these are special vectors and values associated with the matrices that actually reveal the possible outcomes when you measure the spin of a particle.
Okay, eigenvalues and eigenvectors. Those sound a bit technical. Can you break those down a bit further for us?
Yeah, sure. So imagine you have a spinning object and you want to measure its angular momentum. The eigenvalues would represent the possible values that you could get from that measurement, so like specific speeds of rotation. Eigenvectors, on the other hand, are kind of like the axes of rotation. They tell you the directions associated with those specific speeds.
Okay, so the eigenvalues are like the possible outcomes,
Yeah,
and the eigenvectors are like the direction associated with those outcomes.
precisely.
Yeah, that makes more sense.
And in the case of Pauli matrices, the eigenvalues are actually related to the up and down spin states, while the eigenvectors tell us about the orientation of those spin states in space. And these properties really make Pauli matrices incredibly powerful for understanding how spin behaves in the quantum world.
Yeah, that's fascinating. So
Yeah.
you've got these matrices, they have these really special properties that tell us a lot about spin. And now we're
Absolutely.
going to dive even deeper into how those play out in the quantum world.
Exactly.
So stay tuned for part 2,
Yeah, it's going to be exciting.
where we'll delve further into the fascinating world of Pauli matrices.
Looking forward to it. So now that we've sort of grasped the mathematical essence of these matrices, let's explore how they connect to the physical concept of spin. So when you combine Pauli matrices with Planck's constant, which is a fundamental constant in quantum mechanics, they transform into what we call spin operators.
Okay, spin operators, what do they do exactly?
Think of them as like instructions that act on the state of a particle, specifically its spin state. They tell us how the spin of a particle changes over time, or in response to various interactions.
So if the Pauli matrices are like the words, The spin operators are like the sentences that tell us how the spin behaves.
That's a great analogy. And these sentences are crucial for understanding how particles with spin behave in the real world. One classic experiment that really beautifully demonstrates this is the Stern-Gerlach experiment. So imagine shooting a beam of particles like electrons through a specially designed magnetic field. Classically, you would expect the particles to spread out smoothly based on their magnetic properties.
Right, it's like how iron filings align themselves along the lines of a magnetic field.
Exactly. But in the quantum world, something really astonishing happens. Instead of a smooth spread, the particles actually split into two distinct beams, corresponding to spin up and spin down states. And this experiment was really groundbreaking because it provided direct evidence that spin is what we call quantized, meaning it can only take on specific discrete values.
So instead of a continuous range of spin values, particles are restricted to these distinct up or down states.
Exactly.
That's pretty mind-bending.
It is. It is. And Pauli matrices, through their role in spin operators, actually provide that mathematical framework to understand this quantization of spin and how particles behave in magnetic fields.
That's incredible. So these matrices aren't just these abstract mathematical concepts. They have real-world implications for how particles behave at their most fundamental level.
Precisely. And their applications actually extend far beyond just understanding individual particles. They're really crucial for comprehending complex quantum phenomena like entanglement, and also for developing cutting-edge technologies like quantum computers.
Quantum computers, everyone's talking about them. How do Pauli matrices fit into this futuristic technology?
They're essential building blocks. So remember how we talked about the Pauli X matrix acting like a bit flip operator? Well, in quantum computing, we have these things called qubits, which are the quantum equivalent of bits in classical computers.
Right, so qubits can be in a superposition of states, both 0 and 1 at the same time.
Exactly. And to manipulate these qubits and perform computations, we use things called quantum gates. And the Pauli X matrix actually forms the basis for one of the most fundamental quantum gates, the quantum NOT gate, which flips the state of a qubit. Other Pauli matrices are used to create more complex gates that introduce those phase shifts, which are really crucial for quantum algorithms.
So these tiny matrices are helping to power the quantum revolution. What about entanglement? You mentioned that earlier. How do Pauli matrices come into play there?
Entanglement is one of the most bizarre and counterintuitive phenomena in quantum mechanics. It's this strange connection between two particles, where their fates are intertwined no matter how far apart they are. So if you measure the spin of one entangled particle, you instantly know the spin of the other, even if they're light years away.
Wow. That sounds like something out of science fiction. It's like they're communicating faster than the speed of light, which is supposed to be impossible.
I know, it is mind-boggling, and it really challenges our classical understanding of locality and causality. But numerous experiments have confirmed that entanglement is real, and it has really profound implications for our understanding of the universe. Now, Bell's theorem, which is a cornerstone of quantum mechanics, mathematically proves that this spooky action at a distance is a genuine feature of the quantum world and cannot be explained by any classical theory.
So entanglement is not just some theoretical idea, it's a fundamental aspect of reality.
Absolutely. And the proof of Bell's theorem actually relies heavily on the properties of, you guessed it, Pauli matrices.
Of course.
Their mathematical properties are essential for understanding those correlations and relationships between entangled particles. It's a testament to their power and versatility in describing the quantum world.
That's amazing. So Pauli matrices aren't just about manipulating individual spins. They're also crucial for understanding these incredibly complex and mysterious connections between particles.
Precisely. And they have even more applications in areas like quantum dynamics, where they are used to model how the spin state of a particle evolves over time, particularly in the presence of external fields.
So it's like having a mathematical tool. That allows us to predict how the spin of a particle will change under various conditions.
Exactly. By using Pauli matrices within the framework of quantum mechanics, we can really describe and predict the behavior of these incredibly tiny, yet incredibly influential aspects of the universe.
Wow. It's incredible to think that these seemingly simple matrices, these arrangements of numbers, they hold the key to unlocking so much of the quantum world.
I know, it really is. Their elegance and power really lie in their ability to capture the essence of spin and its intricate relationship with other quantum phenomena.
So as we wrap up our exploration of Pauli matrices, what's the biggest takeaway you want our listeners to remember?
I think the most important thing to realize is that Pauli matrices are not just these abstract mathematical objects. They're fundamental tools for understanding the nature of reality. at its most fundamental level. They provide a powerful language for describing the strange and counterintuitive behavior of particles in the quantum realm. And their applications actually extend far beyond what we've even discussed today.
It's like they're this bridge between this abstract world of mathematics
Yeah.
and this tangible reality of the quantum universe.
Exactly. And by studying them, we gain a deeper appreciation for the beauty and complexity of the quantum world.
Yeah, it's been an incredible journey into the heart of quantum mechanics.
It really has. And who knows what other strange and counterintuitive phenomena in the quantum world we might be able to unlock with tools like Pauli Matrices. There's still so much to explore and discover.
Absolutely. And to our listeners, thanks for joining us on this adventure. Keep questioning, keep exploring, and keep that spark of curiosity burning bright.